All right. So if all went well, hopefully you see slides. Well, you see it there. Hopefully now you see slides.
Sure do.
So welcome to the first class of Advanced Reverse Engineering 6580. I'll tell you a little bit about the class, and then we'll get to going. So my name is Stacy Proell. I am a researcher at Oak Ridge National Laboratory. So I am not going to be in Cookeville except on rare occasions. As a result, if you need to talk to me, you need to just make an appointment. Let me know you need to talk to me, and we can chat. My email is there. I'll pay pretty close attention to my email, or at least try to. If you're not getting a hold of me and you're really worried, you can. There's my cell number. You can text me. That's probably the best way to get me is to text me or just straight up call me. There's no TA for this class, so it's just us. We'll have to figure it out, as opposed to me telling someone else to figure it out. We meet at 8 a.m. Cookville time, 9 a.m. Oak Ridge time. I think everybody's got that down. You've got into Zoom, so you don't have to worry about that. All is good. Every year they change the schedule. So this class has been a Tuesday, Thursday class, and then they did that for a while. Then they changed it to a Monday, Wednesday, Friday last year. So I had to redo everything to make it fit into a Monday, Wednesday, Friday class. And of course, this year, helpfully, they changed it to a Monday, Wednesday class, and it's 110 minutes long. That's a long time to listen to anyone talk, especially having to listen to me talk. So I'll try to be sure we have a break and when we get to about the halfway point in the class, thereabouts. Depending on the material, we'll try to take a break. Breaks are good. You should get up and walk around when we take a break, because getting up and walking around is good. And the most important part of the break is that you should come back from the break. There's theoretically a textbook you can get. Whether you can get it or not is a mystery to me. The publisher told us they were out of it. Then they told us they had it. Then they told us they were out of it. So I don't know what the status of it is, if anyone has it. It's a pretty good book. We're going to cover a ton of material that is not in this book, and we're going to go way more in depth for some parts of it, and some stuff that's in the book is stuff we just won't cover. So we're not going to be slavishly following the book. The book is really there to because people have complained in the past. Can I have something to read for this? That's your answer to that. There's going to be some papers. Probably even in the first half of the class, there'll be a few papers that we'll go through, because it's just a graduate class. Slides will be available shortly before the class starts. Sometimes I put solutions to the homework in the slides, and so as a result, I don't make them available before the class. I make them available when class starts, but then you can get to them. We're going to record the classes, and I will do a little bit of editing on them and then make them available. But because after this class, I have to turn around and do real work for a while, it'll be a little while before I can get back to that. So it may take a little bit of time before the recordings show up. But they will eventually show up, even if I have to re-record them. Homework is weekly. Give it out on Wednesday, and it's due the following Wednesday, and it is worth 80% of your grade. So the homework is intended to test practical skills, application of what you're learning, and if you just do all the homework, you could theoretically pass the class without ever taking an exam, which I think is fine by me. There are 2 exams. There's a midterm and a final. They're each worth 10 points, I believe. And they are intended to test the theoretical knowledge for the class. So you can see where the emphasis is. The homework is kind of all or nothing. Most of it's going to be stuff where it should be pretty obvious if you're getting it right or not. I also intend to, whenever possible, automate the grading of it. I have a whole set of insane scripts that go through and chunk up your homework and try to grade it. So you'll be turning that in through iLearn. Hopefully I can automate a lot of the grading because it can be a pain otherwise. And you all will do well with that, I hope. We'll see. Exams are graded out of 100. And everyone wants to know what the exams are like. My exams tend to be a large number of questions for an exam, 15 or so questions. And then I end up counting the best 10 answers. So I give you lots of them. You can choose, you can answer them all, in which case I'll just take your best 10 answers. Or you can answer 10 of them exactly and get really lucky. It's up to you. Both exams are take home. You'll have about a week to do them. So they're exams in some sense. The material is cumulative, so the exams are cumulative too, and they focus primarily on the basic principles that we'll cover. Here's Tennessee Tech's academic calendar. It's been suggested we put it on a slide, so it's on a slide. Here is the part that matters to us. This is the calendar for this class. And so you see we get Monday off. The midterm, I'm planning to give that to you on the 2nd right now of March and get it back on the 7th. So the midterm would come out before spring break, which is 14th through the 18th. And then our final class is at the end of April. And the final will be handed out, and it'll be due at the end of the normal exam time for this class. Hope that makes some sense. Nothing too elaborate or complicated there, I think. If there's anything that's preventing you or hindering your ability to learn from the class the way it's delivered now, let me know. Tennessee Tech has people that can help with this. I can make changes and adjustments. We can work together to try to figure out what the best way is for you to learn the material. And it basically just let me know if you need help or you need some changes or I need to do something to make things better, or if I'm just incomprehensible and you have no idea what I'm saying, let me know. I expect you to do your own work. This is the class where I want you to, just basically the principle is be honest, right? Take responsibility for your own work. Don't take credit for other people's work unless you give them credit, right? Give credit to other people for work that they do. If you collaborate on something, share credit for it. It's not going to matter so much for this class. It's primarily going to be individual work. Okay, so that's it. If you feel like you're really in trouble, before you do something dumb, talk to me and we can figure something out. You're here because presumably you want to learn this stuff. Let's help you learn it and get to the class. So expectations for this class. So I expect you to come to class, which means logging into Zoom, I guess. Read the reading material, when there's reading material, and will be. Do the homework, that's so much of your grade, just do the homework. Email me with questions, and if I don't respond to your email, which is a real thing that happens, text me and I'll get on that. I expect you to know some things. I expect you to know a reasonable amount of C. I don't expect you necessarily to know all of the odd little corners of C, but I expect that anyone in this class could sit down and write a C program to do something, or could read one and understand what's going on. Maybe some C++, that may come up later in the class, and it'd be great if you had seen some C++. I don't expect you to be able to sit down and write something. I don't expect you to know template metaprogramming or any of those kinds of things, but it'd be helpful if you'd seen it. The class is going to be in Linux, so I expect you to be able to work with Linux. And I expect you to know some basic discrete math, and that will come up because we'll talk about type theory and cases where we have to use some math. Sets, functions, relations, predicates, and the basic connectives. At the bottom is a little string of math. Some of the symbols may look a little different from the way you've normally seen them, but you should be able to figure out that says for all x and y, they're in the domain of f, whatever f is. If the ordered pair xy is in K of f, then it is the case that f of x and f of y are equal. And if f of x and f of y are equal, then the ordered pair xy is in K of f. That's the definition of the kernel of a function, for those who deeply care about that kind of thing. Shouldn't look too weird, may look a little funky, but you should be able to understand that and grok what that means. C. The C code on the screen there should not look insane to you. It should look fairly like normal C code. In the past, people have been freaked out by the uint32_t. That's part of the standard types header, which is included by int types header. It's just a precise way of specifying types. You should not be freaked out by it. It's just a 32-bit unsigned integer. There are some other little funny things in here that might be worth pointing out. There are these guys. They come to you the same way from int types. This is the format statement for an unsigned 32-bit integer. So we use that to print a value and so on. So it should be, nothing in this should be bizarre and scary. This is just your typical C code. The only thing that might be kind of bizarre and scary is right here in this line where I have two function pointers. Function pointers may come up a couple of times in this class, and it's worth knowing that if you want to know the type of a function pointer in C, you write down the function prototype, and then you put parentheses around the name, and you put a star in front of it, and you've got yourself a function pointer, the type of a function pointer. A little bit wild, but that's how it works. So this declares a, in this case, a little array of function pointers, and that array is called funs. The name of it's right here in the middle because that's where the name goes in the function pointer. It has two little functions in it, foo and bar, and they're defined up here. That's about as complex as I can imagine anything ever getting in here. It's a 6,000 level computer science course, so I expect you to know some computer science, right? I expect you to know what binary is, what hexadecimal is. When I say high order bits or low order bits, I expect you to know what that means. And I expect you to know how to read and write programs, which is, you know, seriously. I expect you to be able to learn some stuff. We're going to learn assembly language. Assembly language is maybe not the easiest thing to learn, but you can do it. Some maybe a little more computer architecture than you've learned in the past, and some ways in which the computer architecture that you learned in the past might not be exactly how things work, and that may matter. Python, we're going to use Python in this class. So if you haven't learned Python by now, this is your chance. Python is extremely easy to learn. You will not have trouble learning Python, I don't think. If you do, you'll be the first person in years of teaching this class that's had a hard time with it. Lots of learners command line tools, because command line tools are a great way to get information about programs. Maybe a little more discrete math. So over on the right, you see a little schema which says that if the order pair x and y is in the kernel of f, then I am allowed to conclude something about the points being in the domain and the functions being equal to those 2 points. So we'll see that kind of thing come up. So it'll be a little bit of notation that'll pop up, but nothing too fancy, right? We're not going to be inventing any new math along the way. Maybe a little bit of theory as well. So just get ready for that. So I expect you to run experiments and try things and test things out and play with the tools, because that's how you're going to learn this stuff. You're going to learn it by grabbing the stuff, doing stuff with it, and seeing what happens. If you can get the answer to a question by running a tool or running some code, then go do that, right? Go do that. This is intended to be a very practical class. Learning goals. So what would you get out of this? Well, you'll be able to understand assembly language and executable files, how the operating system loads and runs files, because that can matter, how to use command line tools to get information, figuring out the true control flow, figuring out where there are pointers in a compiled program and what they point to. That's the points to problem. It's a great name for that. How to figure out data types. That's a memory shape problem. How to do program instrumentation, taint analysis, symbolic execution, and other techniques, program slicing, and so on that come up a lot. And how to, the main point of all this is how to automate these things. We can only get through building automation for every single one of these things, but we'll get through a lot of it. So I'm going to say binary programs a lot. And what I mean is a program in its native executable form. It may not be the same as a compiled program because many of these won't ever have been through a compiler. And it's not quite the same as an executable because scripts can be executable. So it's a little bit different. They typically rely on your operating system infrastructure because they need to, although a binary program could be part of the operating system itself. Okay, we'll see how that works. So you'll know how to write programs that analyze binary programs. That's the whole purpose of this class. So what is reverse engineering good for? Is there any practical use for it? Sure. Vulnerability discovery is the big one, right? Vulnerability discovery is a place where this pops up a lot. Malware analysis and discovery, that's what I did when I was at CERT, was pick apart malware. That's fun. Code protection, paradoxically, is one way to do it. Optimization. If you want to do, you can actually do optimization on programs that are already written and compiled. That's typically transcompiling the program for a new architecture that requires that you analyze the binary and make changes to it to do that. Code recovery, you may be working for a company someday that's lost its source code, has happened, and they want to know how a particular piece of that code works. For example, the IRS and any of their code. Static and dynamic analysis. Let's talk about that just a bit. So we're actually going to get into some stuff here. So here is a program. And over on the right, it's in C. It's not super complicated. Standard IO, int types. You can ignore that line at the top for right now. We'll come back. We'll get to that in a future class. So int main, argc, argv, and envp. If you've never seen the third argument there on Linux and on Windows, you get past a pointer to all of the environment settings as well. We'll see that in more detail later. So I got a count that's 0. I initialize a number. I go and I read a number from the prompt, and if something goes wrong, I return -1. So it returns out of this whole function. Otherwise, I do this little loop. While number is greater than 1, if it's even, I divide by 2. If it's not even, I multiply it by 3 and add 1. Weird stuff. And then I increment the count. So this may look a little odd. That's that question mark colon operator. I do number %2, so I divide by 2, and that's the remainder. If the remainder is 1, it's odd, and I do this. The remainder is 0, then it's even, and I do this. And I just keep counting until this loop terminates, if it terminates, and then I print out what the count was. And so the question is, what happens when I give it the input 19? How would you figure that out? Anyone want to guess how we figure out what the input of 19 does? What I would do, because I'm lazy, is
compile it and run it.
Yep. I am. There we go, 19, and the output is 20. Wow. Okay, that's fine. So run the program and find out. And when we do that, we put in 19, we get 20 as the output. And we can make this all fancy by saying this is dynamic analysis. And this is dynamic analysis. Dynamic analysis is when you run the code and see what happens. That's basically it. Ran the code and I saw what happened. So what about this question? For what inputs, if any, does the program output 0? And I'd like to know all of them, if you can tell me all of them. Well, this is a tougher question, right? I'm asking about when the output is a certain thing, and it's kind of hard to figure that out because this is kind of weird. We could try different input values, but we might not find them all. How would you figure that out? That seems a little tougher. Well, for that, we can read the code and see if we can figure it out. And one thing we notice is we write out the count right here. So when we get to here, whatever count is, that's going to be the output of the program. Count's initially set to 0 up here. Okay, that's pretty helpful information. And it's only ever changed by incrementing it. So unless it overflows, it'll be 0 if this loop never runs. So if count's never incremented, its value remains 0. 0 is the output. That happens when the loop doesn't execute. That happens when the predicate is initially false. And that happens when number is less than or equal to 1. Nothing too elaborate there. Since number is the input value, doesn't get modified in the loop, that means that this program outputs 0 when the input is either 0 or 1. Pretty simple. So I figured this out by examining the code. We read the code. We sort of traced through it. We figured out count was here. We worked backwards. We saw it was modified here, but only when this predicate was true. So if this predicate was never true, it would not get modified and would remain, in fact, 0. So we can work backwards this way and figure it out. And we'll do that quite a bit. It's program tracing. And we can make this fancy and call this static analysis. It's static analysis because we didn't run the code. Okay, didn't run it. So we have two different techniques here. We have dynamic analysis, where I run the code and now I know what the code does for the particular inputs and in the particular environment in which I ran the code. It's very specific, but yeah, I mean, if I'm running it in an environment where there's not much memory available or where there are lots of other programs running, it may actually behave differently. And so this is a technique that works well when the code's safe to execute, right? It's not malware. If it's malware, I'm running it in a safe container. And I want to know what can happen, right? Just because I observed a particular output when I ran it doesn't mean that the next time I run it, I will observe the same output. Some code can do some pretty nasty stuff, right? There's malware out there that checks what day and time it is, and then behaves differently on a particular time. So that kind of thing can happen. But it's fairly straightforward to do. But doing it and being able to say something meaningful about the result requires some experimental control. You have to set up an environment that you understand, that's repeatable, hopefully, run the code, and then be able to know what you get. For static analysis, now we can know something pretty powerful. We can know what the code does given our assumptions about it. And we can do this for code that's not safe to execute and that may not run in a reasonable time. And again, for which we want an answer like, does it ever give this output? Okay, so those are the kinds of things we can do. Static analysis can be really, really hard. And we'll talk about just how hard it is later on. And most of what we'll do in this class could be categorized as static analysis. We do a lot of static analysis. Doing this requires a model of the computation. What does that mean? That means you have to have some kind of an informal or maybe even a formal model of how the machine behaves and what each instruction means in order to be able to play this kind of game. Dynamic analysis is an experiment. Okay. And static analysis is basically building a model of what the program is going to do. If you want to do them in a meaningful, useful way, it needs a little bit of discipline around them, so the results will be useful. And neither of those is the program itself. It can still behave in a way that you haven't accounted for. It can absolutely surprise you. And that can be because computation has physical effects. And if I set things up correctly, I can take advantage of the physical effects of computation to do weird things. It can be because I know that there are errors on the incorrectly implemented opcodes on the processor, or there are bugs somewhere in the operating system, and I can take advantage of that. And so static analysis might fail. It can be a mess. But those are the techniques that we're going to have available to us: dynamic and static analysis. So we're going to talk a lot about the full. I'm going to close my door. Hold on. Got people here this morning to do some work, and the dog roaming the building looking for food. So we're going to talk a lot about the full range of behavior of programs, and let's think about that just a little bit more. So back to that program we looked at earlier. The output's 0 when the input is an unsigned integer that is less than or equal to 1. That's what we said. Input is either 0 or 1. Those are only unsigned integers less than or equal to 1. And the question is, was that unnecessarily pedantic? What if I didn't give it an unsigned image? What if I gave it something else? And we could try that. Right? We can pop down here and we can try -100. So we do check scanf to see if it comes back with a result that's less than 0, and if so, it returns -1. Let's see what we get from -100. We get 192. Okay, let's try it for something that's not a number. That might be better. Let's try it for Frank. And the answer is 127. So that's kind of weird. So there we go. So up here, they try it for a couple different values, and they get some answers similar to what we got. And the question is, why isn't this catching the problem right here and stopping it? So one thing we can do is we can modify the program, and we can see what is actually being read. And so for -12, we get that number. That's the number it thinks it's read, and the answer is 224. For Fred, we get this number, and that's the number it thinks it read, and the answer is 96. So those are kind of wild right there. We get the same thing, -12 and Fred. Let's try it. -12. We do not even close to the same thing, right? 224 and 96. Well, we get 224 if we get the same answer for that, but we get 187 for Fred, whereas we got 96 up here. And if we keep trying Fred, we get different numbers, seemingly at random. So what's going on there? So again, we can take a look here. Why is our scanf check not working? It's because scanf only reports an error when you have an end of file that's unexpected. Otherwise, it tells you the number of things that it successfully read, which in the case of Fred, I'm guessing is 0, which is not less than 0. And so we don't catch it that way. So if we came out here and we tried just a straight up Control-D, and also actually looked at the output value, there we go, we see 255. Is that -1? Turns out in the 8-bit world it is. So, all right. So again, we can see the exit value. We can see it here. Otherwise, it reports the number of values that it parses. If it doesn't parse anything as a number, it just leaves number unchanged, but number is never initialized. And in the wonderful world of C, that's a good way to get some random garbage into the variable number. And that's in fact what we see. We see some random garbage come through number and be output. It's undefined behavior. So another way to think about this is your program has inputs we know about and outputs we see. And it may also have inputs we don't know about and outputs we don't see. And we run a program for dynamic analysis, we have to establish some experimental control. Right? What are the programs? Let's run it in a container. Let's see what it accesses. Let's be sure that it's always getting the same results, so that we have some control over it. And we have to account for the fact that there are things that are probably changing as we do this. And we have to try to understand which outputs are actually observable and which are unobservable. Okay. For static analysis, the same thing is true. You have to establish a control boundary around the program, specify the things we can control and the things we can't control, just accept the things we can't control, and what we can see and what we can't see. And have to consider all those cases. So I have to consider the full set of cases of behavior of the program. So back to our little program. If we enter something that's not an unsigned integer, we get random stuff. What if we enter something that's outside the 32-bit range? And okay, we can do that. So the 32-bit range goes from 0 up to this big number. What if we enter one more? So instead of 95, it's 96. In that case, we get a 0. So it looks like it's wrapped around. And that would let us help, that would be evidence that the input's modulo 2 to the 32. And another good question is that always true? What's the maximum input scanf can read? So we can go read the documentation for scanf and find out that no one tells us that. And so we can try some experiments. And if you put in a big number, this is the maximum 64-bit unsigned integer. What if you put in that? Well, if you put in that, that's what it thinks we entered, and that's the answer. So it still looks like it's wrapping around. And if we try one on either side of that, we get this. It goes down one. But here, we just get the same result as if we had the 15 on the end. So it seems like scanf parses up to a 64-bit integer, and then it performs modular arithmetic based on whatever it parsed. And if you dig into the code, that's what it's actually doing. So to figure all this stuff out, we used a combination of static and dynamic analysis, right? We ran the program, we looked at it, we ran it, we looked at it some more, we looked at some edge values, right? Limits around 2 to the 32nd and 2 to the 64th. And this is a perfect example of the kind of analysis that we'll have to do to understand programs. It's the perfect example of the kind of thing that you would do if you're trying to figure out what some unknown program does. The trick is now, how do we automate that kind of analysis? And as we get near the end, we'll talk about concolic analysis, which is a combination of both static and dynamic analysis. The point of all this, the reason this is interesting, is that vulnerabilities typically occur when you have two things that meet, right? Two systems are plugged together, two libraries are communicating, something else is happening. Someone is interacting with your system, right? It occurs at the edges of components of your system. And that's where you typically would find vulnerabilities. And so all this is relevant to that. So a question worth asking is, what, if any, are the limitations of reverse engineering? Are there any limits of what I can and can't reverse engineer, and what are they? And for that, we can consider, what are some of the things we know we can do with this? Well, we know we can figure out what programs do. We figure out Alloy does all the time. It turns out you can often figure out who wrote a program. A disturbing number of times you can figure out who wrote it, where they wrote it, what compiler they used, what the options were used, because compilers love to shove metadata into your executable, and lots of people forget to clean that. So there have been cases where people's personal identifiable information has showed up in malware, and that for some reason delights me. So you can find those kinds of things out. But are there limits? Can you answer any question about any program? Well, answering questions about programs is the domain of computing theory. Okay. And so what do we learn from computing theory? Well, okay, now we've got to go back and talk about Turing machines. So a string is accepted if when you put that on the input tape of the Turing machine and you run the Turing machine halts in an accepting state. You got to remember all your Turing machine stuff now. The set of all the strings for which the Turing machine halts in an accepting state is the language of M. The set of all strings that are accepted by M is called the language of M. And we say those are recursively enumerable for technical reasons I don't want to get into. So you can think of a Turing machine as encoding what we would call a partially computable function. It's computable because there's actually a process, right, the Turing machine process, to determine the output for each input, right? And that is, put the input on the tape, run the Turing machine. Right? Turing machine is deterministic. It's going to look at the tape, it's going to look at its current state, it's going to move to a new state, write something to the tape potentially, and it's going to run. And when it halts, if it halts, it'll either be in an accepting or not state, and it might not halt. What if it doesn't halt? Well, then that string isn't in the domain of the Turing machine, and it's a partial function. Okay, so there's a set of all strings. There's a set of all strings which the Turing machine actually halts, and then there's a set of strings which it halts in an accepting state. There you go. A property of Turing machine languages is a subset of all the languages. It's a subset that satisfies a particular property. It's getting pretty abstract, but keep with me here. So I'll say a property is decidable if, for any Turing machine language, I can tell you whether or not that language is in the property P, right? A property is a subset of all the languages. And so it's the things that are in the property are themselves languages. And the property holds for a language if that language is in the characteristic set for P. A property of Turing machine languages is trivial if it's either true for all languages or false for all languages. So here we go. What's an example of a trivial property? A trivial property of the Turing machine languages is the language can be recognized by a Turing machine. That's true for all of the languages. So that property is the set of all Turing machine languages. Great. A non-trivial property is something like the language is finite. So I can produce a Turing machine that accepts only a single string. That's clearly a finite language. And I can produce a Turing machine that accepts all strings. That's an infinite language. And so a non-trivial property is a property that's true for some, but not all. Okay. If it's true for none, then it's trivial. If it's true for all, then it's trivial. If it's an interesting question, right? If sometimes it's true and sometimes it's not, then that's a non-trivial property. And that takes us to Rice's theorem. And if you want to read the original paper, it's cited at the bottom. Rice's theorem tells us that any non-trivial property of Turing machine languages is undecidable. So there you go. If you have an interesting question about programs, it's undecidable. There you go. It applies to semantic properties, not syntactic. So if you want to know how long is the source code, does it contain the letter Z, those don't, Rice's theorem doesn't apply to that. If you want to know, does it ever print my name? Maybe it does, maybe it doesn't. Some programs do, some programs don't. Therefore, it's undecidable. So that's a pretty strong statement. So how do we do anything in the presence of such a strong statement? Well, you can prove Rice's theorem from the halting problem. If you want to know how to do that, Wikipedia is your friend. They actually have the derivation of it over on Wikipedia. So if you believe the halting problem, you end up obligated to believe Rice's theorem. And you can, I think, probably see how they are very close together. And so back to our little program, we asked the question, does the program ever print 0? Well, some programs print 0 and some programs don't. So the question of whether a program ever prints 0 is undecidable. So how did we decide that our program does? I mean, doesn't Rice's theorem tell us we can't know? And even more so, I could put this in a larger program and I could halt when it prints 0, and I could then and never halt if it doesn't print 0. Okay, well, I'll only halt when it prints 0. So that larger program only halts when the smaller one prints 0, so it becomes a halting problem. So I can play this game all day, right? These are things that the theorems tell us we can't know the answer to these questions. So how is it we figured it out? Because we did figure it out. Well, what these things tell us is we can't write a finite decision procedure, a program, that answers the question for any other program. It doesn't tell us I can't figure it out for a particular program. It's not funny semantics. That's really what those theorems tell us. They tell me you can't write a piece of code that if I feed it any other program, it'll answer that question. It doesn't tell you that you can't figure it out, and it doesn't tell you that you can't figure it out for a particular program. Okay. So we have this guy right here, this while loop. While number is greater than 1, either multiply it by 3 and add 1 or divide it by 2. And here's the question, does this program halt for all inputs? Again, this sounds like the halting problem, right? So each time through, the number might go up or it might go down. And we want to know if it halts for all inputs. It turns out, and you can watch this YouTube video if you're curious about it, it turns out this is something called the Collatz conjecture. And we don't know. We don't know if for all numbers, it eventually reaches 1. We just don't know. So what we have here is a case of the halting problem. I want to know if a program halts on all inputs. And I want to know that for a program that computes something that we don't know the answer to. Like mathematically, we don't have an answer to this question. So what do we do? Oops, I don't want to play the video. No! I want to skip ahead. There we go. The video is fun. You should watch the video. Well, it turns out we can totally know the answer to this question. We can answer it definitively. There's a finite number of unsigned 32-bit integers. That's what number is. So even if it's in the chaotic uninitialized state, it's still one of the 2 to the 32 numbers. It might take us a long time. Suppose it takes us a second to check each value. That might take 136 years. What if some don't terminate? Well, they have to eventually revisit a number that's in this set, right? They have to be in they are in this closed finite set of 2 to the 32, which is admittedly a lot, but still a finite number of values. So even if it takes hundreds of years to check them all, or thousands or millions or billions of years, it's still decidable. It's still a finite decision process. And in fact, in this case, we know it does because people have checked all the Hailstone numbers up to 2 to the 60th. So since we're only 2 to the 32nd, we know that every input of this program will halt. So we've cracked the halting problem for this particular program, even though the underlying question is one that's unsolved by mathematics, which is, I think, pretty cool. The idea is that Rice's theorem of the halting problem preclude writing programs that answer a behavioral question, right, a semantic question for every program, but not for a particular program and not for a large and potentially very interesting subset of all programs. So why does all this matter? you're going to be writing programs that analyze other programs. And so all these limitations apply. And the challenge is to be able to do this for programs that are interesting and worthwhile, right? It's easy to write a program that never halts. It's more challenging to write a program whose halting is undecidable. Considerably more challenging to do that. All right. So let's switch and talk a little bit about reverse engineering, and in particular, what you mean by it. So my claim is reverse engineering of software is a process for answering questions, right? You ask me how many bytes are in the program, and I tell you that counts. That counts. You ask me, is this string in the program? And I run strings and see that counts. Clearly, you want to ask more interesting questions than that. But basically, that's it, right? Reverse engineering is the process of just answering questions about programs. It's not figuring everything about the program out, because you'll never do that, right? The program is the program. Nothing else is the program. Everything else is a mental model or a mathematical model or some other kind of model of the program. Answering questions, that's what it means. We can try to make it a little more formal and see if that leads us anywhere, and it will later on in the class. Let's say we have a question about our program. And given the program, we want to know if that question is, the answer is yes or no. So maybe we can run the program, or maybe we can read the program, or do a combination of both. One way that we will fall back on a surprising amount in this class is that it will say, well, you know, answering question Q for this program is hard. It makes my head hurt. I don't like it. It's making me annoyed to think about it. Why don't I answer a different question for a different program? That's easy. Okay, so what we do there is we build a model. We have a new program P prime. We might have a new question. Now our question is Q prime. And so we get the answer to a different question for a different program. We do that because it's easy. Like, well, I don't want to answer the question if it halts. Maybe I can just answer this other question over here for this other program. And we'll do a lot of that. That will be relevant if the question answered for the other program tells us that the answer is also, when it's true, tells us that the answer is also true for our relevant question and relevant program. Okay. Or maybe if it's false, it tells us the answer is false. It would be incredibly rare to have both of those two statements be true. Dr. RP did. Good reason to believe one of the following statements, one of those two. Then it's useful to do that. Okay. So throw this in because it's relevant. All models are wrong, but some models are useful. And sometimes for a really complicated program, the model that you need to solve in order to answer an interesting question turns out to be a really simple model. And that's great when that happens. So we're about to get into part 2, but before we do, we're at about the halfway point. Let's take a 5-minute break, and I will see you back at what, 10:02. So let's get into part 2. It's always good to switch gears after you throw a lot of unexpected math at people. So my initial disclaimer. So I'm not a lawyer, and you're probably not a lawyer either. If you are a lawyer, that's great. But we're probably not lawyers. But we're going to be doing some things where the application of that knowledge has consequences. And so let's talk a little bit about the legality of reverse engineering. So here's a slide with lots of words. And you can read this at your leisure. In fact, you can read all of the of this section of the U.S. Code. If you are interested in doing that, it really talks about when it's legal to reverse engineer something. There's a link to the whole text down here. But you see the word interoperability called out right here, right? Circumventing a technological measure to control access when it's necessary to achieve interoperability. So you could reverse engineer part of a piece of code, and you can do that for the purpose of being able to interoperate with that code. A person may develop and employ technological means to circumvent a technological measure, circumvent protection afforded by a technological measure. And yes, compiling code counts as a technological measure intended to protect code. Weird. For interoperability. Okay. So the word interoperability appears a whole bunch of times in here, and that's basically the lesson here. If there's a piece of copyrighted code or copy protected code, what are you allowed to rip that apart when you're doing that to interoperate with something else? Are there limitations? Sure. So it can be legal when you're doing it to enable interoperability. And an interesting case that's on point is this one in 2003. Bowers and Basic Technologies had this little fight over patent and copyright infringement and breach of contract. Baystate breached the contract by reversing Bowers' program because they had agreed to a shrink wrap license that said they wouldn't. So this case is notable for a whole bunch of reasons. One of them is shrink wrap license being enforced. That's, that's scary in itself. But also the shrink wrap license gave them a right they wouldn't otherwise have. Okay. License agreements can preempt fair use rights and potentially expand the rights of copyright holders beyond what's codified in U.S. federal law, right? The only reason we're going to let you have this program, but you have to agree that you won't reverse engineer it. Well, I'm allowed to reverse engineer it for the purpose of interoperability, which is what they were doing. No. The only reason we gave it to you is because you said you wouldn't do that. So there you go. You have to be aware of all the things that are involved in this. One of them is license agreements, which can actually preempt or modify your rights in a variety of ways. You want to know more about this? The Electronic Frontier Foundation has a whole big long page of information about how to limit your legal risk when you're doing reverse engineering of commercial software. And what's risky? Violating your contract terms, violating an NDA, stealing software, etc. Those are things that are legally risky, shockingly, right? Violating agreements, stealing stuff, doing stuff you're not authorized to do. Okay. It's legally risky to bypass a technical protection measure, right? Okay, so that would be something like figuring out how to bypass access controls in the operating system on a phone, right? Rooting a phone. It can be risky to copy code you find through the process of reverse engineering into your own code, right? Stealing someone else's code. It can be very risky because even if you do it in public, there can still be copyrights and even patents around parts of code. I don't want to get into whether or not code should be patented, but that can be risky. Okay. So the basic guardrail here is don't violate agreement. If you willingly enter into an agreement that says I won't reverse engineer your code, then don't do that. I think that's fairly straightforward. Vulnerabilities?
I have a quick question.
Yeah, sure.
Are the penalties for that kind of violation like generally just like monetary, or are they like go to jail kinds of penalties, or
They're
does it,
usually
like,
monetary. This is in the civil code. So as opposed to the, I'm getting this wrong. Again, not a lawyer, but yeah, it's typically monetary if it's a fine of some kind, right? If you violate, it's like if you violate any other agreement.
sure,
If you
sure.
violate
So
an agreement with a contractor, they're going to sue you. If the contractor violates an agreement with you, you're going to sue them. Same kind of thing.
so this kind of goes into, like, if you're working for like a vulnerability research firm or something like that, doing reverse engineering, they would probably carry some sort of legal insurance or protection for their employees.
That could be theft. So if you right, you could be accused of theft of trade secrets,
Mhm.
and that does have criminal penalties, right? Because if the trade secrets are above a certain value, then they can go after you for things like grand theft.
Yeah. Okay.
And that has happened. And there are some cases. The EFF is a great resource for cases and outcomes, and you can have a look at that. But yeah, that's the kind of thing you can do. And some NDAs can have fairly serious penalties. If you've ever held a clearance, there are some pretty severe penalties for breaking that particular set of NDAs. So, vulnerability disclosure. So if you find, let me go back. If you find something, should you say something about it? Well, many companies now, once a time when they did not, but many now have vulnerability disclosure policies, but not necessarily all of them, and they don't necessarily cover everything. So you should look for a safe harbor policy if they have one. And sometimes they have a bug bounty program. Sometimes you can get paid to disclose your vulnerability to the company itself. Sometimes you can get paid more if you disclose it somewhere else, but in general, that's legally risky, right? Okay. So picking on Dropbox, they have one. And it's interesting because you can read about which things are in scope for the bug bounty program and which things are out of scope for the bug bounty program. They won't pay for anything. And there have been cases where people have fought over that. If you go to HackerOne, you can find a nice listing of companies that have these programs, and at the very least have safe ways for you to report vulnerabilities that you find. And if you're going to disclose a vulnerability, you really should disclose it to the impacted party before you disclose it, let's say at DEF CON, right? It's fine to go to DEF CON and say, hey, I found this great vulnerability, but guess what? You can't use it anymore because I've already disclosed it to Yahoo and they fixed it. There you go. So there may be specific disclosure processes that will protect you, and you should look into that before you publicly disclose a vulnerability. Again, Electronic Frontier Foundation has a great fact on how to limit your legal risk when you're reporting a vulnerability, right? Don't try to extort money from the company, right? If maybe they'll pay you, that's great. But you can actually get yourself in trouble by what appears to be extortion. And there's a little link there to the GameSpy case where that is exactly what happened. All right. So you don't just call up and say, I found this vulnerability. If you pay me all this money, I'll tell you what it is. That's not going to turn out well. That's not legal. If you're under a non-disclosure agreement, you may not be allowed to publish at all. Courts have been very likely. Courts have been consistently holding researchers to promises to maintain confidentiality. And that can be pretty serious, right? I mean, if you certain kinds of vulnerabilities in certain environments are really very serious, and they can actually be born classified. So if you find a vulnerability in certain systems, that vulnerability is born classified, and because you're in that environment, because of the kind of system it is, you need to exactly follow the correct set of procedures to disclose it, to avoid getting in very serious trouble. You can publish information to the general public, but don't publish information directly to people you know intend to break the law. In other words, don't sell the vulnerability you find on the dark web to someone who wants to use it for their ransomware campaign. Disclose to the vendor or system administrator first and wait a reasonable and fair amount of time before publishing to a wider audience. Have there been cases where people have disclosed it, they've waited, nobody's fixed it, and then they disclose it to the public? Yes. To my knowledge, no one has been sued for that. If they're not fixing something that's a serious critical problem, sometimes shame will move them, but again, be careful. And considering having a lawyer negotiate an agreement with the company under which you'll provide details. That's a bit extreme. Lawyers are not cheap, but their main purpose of a lawyer is to keep you from getting yourself into more trouble than you're already in. All right. Consider the risks and the benefits of describing this with proof of concept code. So I've seen cases where a vulnerability is disclosed. Later that day, there is code in Metasploit, code for Metasploit that exploits it. And then a month later, and I'll not be coy, a month later, Adobe fixes it. And so for that whole month, there's this serious vulnerability sitting out there that is really easy to take advantage of. So be careful about that. All right. Consider the impact of what you're doing. All right. So all these bullets are basically think about who you're disclosing it to and what the impact of disclosure will be. There are bug bounties. Sometimes if you're not careful and you don't follow the rules, the companies will come after you. There's an Ars Technica article from 2017 where they decided that this wasn't something they wanted to pay a bounty for, and they didn't like the way that you read the article. So you might consider whether you have a duty to disclose the vulnerability. And that means you need to think about the consequences of disclosing it. And you need to remember that if you can discover it, the world is full of smart people. Somebody else can eventually discover it too. It may have already been discovered. It may be being used right now in malware. Right? A lot of times when we find these vulnerabilities, we go back and look at a malware corpus and say, is this in use? And we find out, yeah, it's been in use. So you should think about the consequences of disclosing it. You should think about the consequences of not disclosing it. Who is hurt, who's impacted by each of those different decisions, right? To decide whether you have an ethical duty to disclose. I won't get too deeply into that. You can buy your own copy of Peter Singer's Practical Ethics and read that. If you're a federal employee, or you're applying for federal employment, and you lawfully disclose information, I put lawfully in italics because it's important. If you lawfully disclose information that you reasonably believe violates the law, is gross mismanagement, it's a waste of funds, right? Waste, fraud, and abuse is the whole trio. An abuse of authority, or poses a substantial and specific danger to public health or safety, right? It can't be, this could be tragic if these sets of things happen. It needs to be specific. Then you qualify for whistleblower protection. There's a lot going on there, right? Lawfully disclose, right? So you can't just go on CBS and disclose it, right? You may have to disclose it within the system. You have to have a reasonable belief that it meets one of these criteria. And it has to stand up to this, then you can be eligible for whistleblower protection. So Lots of stuff going on there. You can read the statute on that, but it turns out when you read it, you find out there are lots of provisos associated with that. It's not an automatic thing. So the point is, you have to evaluate the consequences of the vulnerability and the consequences of disclosure to everybody, right? To yourself, certainly, to the public at large, to each of the parties that's impacted by the vulnerability. To think about the consequences when you're trying to decide who to disclose it to and whether to disclose it. All right. Shift gears again. Class environment. What I mean by that is we're going to be doing a lot of stuff with code, and we're going to be doing it in Linux. So every year I sort of tinker with the idea of maybe moving to Windows. Windows is getting pretty attractive for a lot of reasons, but again, not everybody has Windows. The first year I taught this class, I think most people in the class had a Mac. And so, all right, well, not everybody has a Mac, not everybody has a Windows machine, but everyone can have a Linux computer, right? Linux is free, as in beer, so you can go get it. VirtualBox exists. In fact, there's now a free version of VMware you can run. So you can go get VirtualBox or VMware, and you can build a VM if you're running Windows. You can run the VM under that. If you're running a Mac, you can run the VM under that. And you can, in fact, all have an Ubuntu 2004 or 2010 if you're adventurous environment. Okay. We're going to add a lot to this as we go along, so there'll be a lot of software that gets added to this environment. But you can all have Linux, and you can have it without expending any additional money, and that's good. So Linux is the environment for the class. All right, that's it for today. The next time we meet, we will talk about computer architecture. And since this is a Monday, there's no homework for you today, but next time is Wednesday, and I'll assign the first homework.